So we are going to see what is magnetic field and Barrett's law and its applications. So first of all, we need to understand what is magnetic flux density. So by definition, it is said that magnetic flux density is the magnetic lines of force passing normally through unit surface area. Like this is a unit surface area A. Okay, unit surface area A. So from this, if the magnetic lines of force are passing normally, like this, the magnetic lines of force are passing normally. So how many lines are passing? That's called the magnetic flux density. Means the number of magnetic lines of force passing normally through the unit surface area. That is called magnetic flux density. So by using Barrett-Savage's law, we calculate the magnetic flux density for symmetrical and unsymmetrical conductors carrying current. So for that, we just need to draw a conductor which is carrying current and the specified point at which the current magnetic flux density is to be determined. So for that, we just need to draw a conductor. See, this is a conductor. Conductor, which is XY. It is carrying current I. It's carrying current I. And we need to calculate the magnetic flux density at point P. This point P is in the magnetic field of this conductor, because whenever current passes through the conductor, magnetic field is produced. This experimental result was given by Ørsted. He said that whenever the current passes through the conductor, the magnetic field is also produced. Electric field produces magnetic field. So whenever this current will pass through the conductor, magnetic field will be produced. Let P be a point in the magnetic field of this conductor. So at point P, we need to calculate the magnetic flux density. Okay. So this point P, now this point P is at a distance, it is at a certain distance from this conductor. Okay. So we'll say that distance to be R. Simple. XY is the conductor, Y is the current passing through it, P is the specified point where the flux density is to be determined. This is at a distance R from the conductor. Let AB be the small elemental length. Okay. So there is a trick for this. All the applications and all the uses of Barrett-Savage's law. When we write that let P be the specified point, then after that we always write let AB be the elemental length. A trick है बस. So see, P is the specified point, and then let AB be the small elemental length, and this point P is joined to C, where C is the midpoint of AB. It's simple. AB is the elemental length, P is the specified point, so C is the center of AB. C and P are joined such that CP equal to R, and the angle between them is theta. So theta is the angle between the elemental length and the line joining the elemental length, midpoint of the elemental length and the specified point. This is the basic figure. Looks confusing, but it's very easy. Okay. So now the description, when you see the notebook, the description is almost like that. Let us consider XY is a conductor through which current I is flowing. Let P is the specified point within the magnetic field of conductor where the flux density is to be obtained, as I said. Then let AB be the elemental length, whose length is dl. I missed this point, that the length of the elemental length is dl. Let AB equal to dl is the small elemental length. And now for this experiment, Barrett-Savage they experimentally proved that they saw, according to the observations, they said that this flux density at this point P, the magnetic flux density at this point P, it is directly proportional to some of the factors that I'm going to discuss now. It is directly proportional, first of all, to the current passing through it, i.e. dB, which is the small flux density, because because at point P we are calculating the flux density due to the small elemental length dl. So the small flux density, it is directly proportional to the current flowing. Okay, and then dB is also directly proportional to the sine of the angle between the midpoint of the elemental length and the line joining the elemental length and this point P. So it is directly proportional to sine theta. Okay, and then it is also directly proportional to this elemental length. So dB is directly proportional to elemental length, and it is inversely proportional to the r square. So I'm going to say this all again right now, just to be clear. So see, till now I just said this much, that figure, I explained the figure, and then I'm going to repeat this now. I explained the figure, and then Bart-Savart, they both experimentally they saw that is dB, the small flux density at point P. Now why is it small flux density? This question might arise, because see, at point P we are calculating the flux density to the small elemental length dl, so the flux density is small dB. So they saw that dB is directly proportional to I, the current flowing through that. Keep noting, it will be much easier. dB is directly proportional to I, dB is directly proportional to dl, the length, dB is directly proportional to sine theta, and dP is inversely proportional to r square. When we combine this all, we get dB is directly proportional to I dl sine theta by r square. Obviously a proportionality constant k will come there, so dB equal to k I dl sine theta by r square. In CGS system the value of k is 1, only in CGS system, but in SI system the value of k is u0 by 4 pi. So this is the value of k in SI system. So the basic formula will be mu0 by 4 pi I dl sine theta by r square. So now this becomes the formula for the small flux density at the specified point due to a current carrying conductor. To obtain the total flux density, i.e. capital B, this is the small flux density. To obtain the total flux density, we will integrate this equation within the respective limits, and the limits they depend on the type of conductor used. We'll discuss it in the applications now. It is very easy. So this was all about Bart-Savart's law. Now it's applications. So first application, it is about the circular coil carrying current, but at the center of the circular coil, i.e. the flux density at the center of the circular coil. So see, first of all we draw a circular coil. You can see in your notebook there is a circular coil drawn. This is a circular coil. This is a circular coil. Okay. So current I is passing through this. Okay. We have to calculate the flux density at the center of this. Center is O. Now this radius of this. Now radius of the circular coil is A. Will not write R for now. No, you can write R, but it will be easy if we assume this as A, because basically they assume it as A. So let us also assume it as A. Okay. So this is a circular coil with center O and radius A. I is the current flowing through it. We need to calculate the flux density at O. And I said, after we write that we need to calculate the flux density at this specified point, we write about the elemental length. So let AP equal to DL is the small elemental length. Okay. Obviously the specified point is always connected to the midpoint of the elemental length. So it is connected to the midpoint of the elemental length C. Easy. And this is all about the figure. And then we'll calculate the flux density at the center of the circular coil O. Okay. So you understood the figure? So now let's go for the description. This is all about. Let's consider circular coil of radius A. Through its current I is flowing, as I said, and has O as its center. Okay. As the current flows through the coil, magnetic field is produced. As I said, whenever current flows, then magnetic field is also produced. So magnetic field is produced. Now O is the point where we have to calculate the flux density. So AB equal to DL be the small elemental length. C and R joints as the CO equal to A. Here the angle between them is 90 degree because they are perpendicular. Last one we saw it was theta angle because we needed to prove here that theta angle is 90 degree. So it is 90 degree. It means that this CO and AB, they are perpendicular. Okay, they are perpendicular 90 degree. Now, so the value of flux density at point O according to Biot-Savart's law, as I said, it is dB equal to mu naught by 4 pi I dl sine theta by r square. This is the value of flux density, as I said, according to Biot-Savart's law. So according to Biot-Savart's law, it is dB equal to mu naught by 4 pi I dl sine theta by r square. But here radius r we have denoted it as A, so it will be dB equal to mu naught by 4 pi, keep looking at your notebooks, mu naught by 4 pi I dl sine theta by A square, isn't it? Okay, so now again theta is 90 degree, so dB equal to mu naught by 4 pi I dl sine 90 degree means 1, so it will be I dl by A square. Okay, this will be the value of the small flux density. Now to calculate the value of the total flux density at point O due to the entire length of the conductor, you have to integrate it under the respective limits, and here the respective limits will be the perimeter of the circular coil. The perimeter. Okay, so see, the perimeter of the circular coil is 2 pi r, so it will be 0 to 2 pi r, the respective limits, 0 to 2 pi r, because we are calculating flux density due to the entire length of the conductor. So see, this is the entire length of the conductor. Okay, this is the entire length of the conductor, so you have to calculate the flux density due to it from starting from 0 to 2 pi a. This is the entire length of the conductor, like this. Okay, so that's why we use the limit 0 to 2 pi a because the perimeter is 2 pi r, but we have assumed the r to be a, so it is 2 pi a. Okay, so now integration I'll show you step by step. Okay, so see, so first of all, okay, so as I said, I'm going to show you the integration step by step. So see, our final expression was dB equal to mu naught by 4 pi I dl by a square. This was our equation 1. Now we need to calculate the total value of the flux density at the center of the coil due to the entire length of the conductor by integrating it, and as I said, integration will be from 0 to 2 pi a. So see, total flux density is 0 to 2 pi a and this dB. Okay, so 0 to 2 pi a. Okay, it's gonna take not much time, it's very easy. So it will be 0 u naught by 4 pi I dl by a square. Now obviously in integration all the constant terms come out. Now see how we need to categorize the constant terms. See, u naught is a constant universal. Actually this whole is a constant because you know it is a k equal to mu naught by 4 pi, and k is a proportionality constant, so this whole will come out. Now see, I is the current will always be constant because that same current is passing through the entire coil, so I is also constant, and A is the radius is also it's not gonna change obviously, so is also constant. So only the thing remaining inside the integration will be dl. so it will be 0 to 2 pi a dl. Rest all will be out, mu naught by 4 pi I by a square. Now as per the formula, of integration, dl का integration होगा l, because see, according to formula the integration is na, so dA, its integration will be a. Okay, the integration of d something, anything d, it will be that particular term. Like if it would be dn here, dn, then the integration would be n, but here it is dl, so integration is l. We need to memorize the formulas too, it will be much easier. So see, u naught by 4 pi I by a square, and then integration is l. Now it is respective limits one integration, so 0 to 2 pi a. Okay, now see, we know first we need to put the upper value and then the lower value. So let's do this page. So it will be u naught by 4 pi I by a square. Now upper value first of all 2 pi a minus the lower value, isn't it? The upper value minus the lower value. Upper value will be kept there, minus lower value. Okay, now see, then we'll go for the calculation. U naught by 4 pi I by a square 2 pi a. Okay, so see, a square and a cancel, pi and pi cancel, this will be 2, this will be 1, so the final value will be u naught I by 2a. This will be the total value of the flux density at the center of the circular coil carrying current. Okay, now if there are n such number of circular coils, n, see, one thing I want to say, that there is a confusion between number of turns and number of circular coils. Whenever there is the number of turns, wherever, not in this chapter, wherever when there is number of turns, we use small n. Okay, and whenever it is number of circular coils, it is capital N. Now what is the difference between number of turns and number of circular coils? So see, turn is basically this is a turn, like a solenoid or any conductor can have this much, like this turns. Okay, these are the turns, number of turns, small n. But the coil is this way, like it is somehow like turns can also make the coils like this way. Okay, this is a coil, this entire is a coil, and if this is a coil and more coils are placed upon it, like this, coils बढ़ते गया, so this is the capital N, number of coils. This is the basic difference between turns and coils. So if there are n such number of circular coils, then obviously its value will be u naught n I by 2a. This is the value. Now this is all about the flux density at the center of the circular coil carrying current. Okay, so that was the first application of Biot-Savart's law. Now let us go for the second application. It is also about the circular coil, but this time we are calculating the flux density on the axis of circular coil carrying current. Okay, so this one is quite complex and confusing. It is very easy. So again, I'm gonna say this to you step by step so that you can understand everything, because this one is complex. So let's start it. So first of all, we'll draw the figure. This time we are again drawing the circular coil, but this time we need to find on the axis, so we'll draw it like this. Now basically this figure is of a circular coil, like this is a coil, okay, circular coil, but when it is turned like this, so it is the figure of this part. This is circular coil as we drew it in the first application, but now it is turned this way. So this is the circular coil, the peripheral part of the circular coil. Again, O is its center, and as I said, A is its radius. We are not assuming it R, so that we do not get confused, because here R is used for something else. So A is the radius. Always remember, A is the radius of circular coil. Okay, in both the applications, A is the radius of circular coil. So see, A is its radius, current I is flowing through it. Okay, you can make it on either direction, you can make it this way or this way, any direction. See, now we have to calculate the point we have to calculate the flux density at point P, which is along the axis of the circular coil. So this is the axis of the circular coil. Okay, so here we need to calculate at this point P. Let us assume this point P. Here we need to calculate the magnetic flux density. As the current flows through the coil, magnetic field is produced, and P lies on the axis of that magnetic field. So now see, it is very easy. Now I said always after writing the specified point, about specified point, like P is the specified point, we need to mention about the elemental length. So see here, elemental length will be this. Okay, A and B, and always the midpoint of the elemental length is connected to the specified point. So it is connected to the specified point. AB is the elemental length. Okay, like this, it goes like this. I know it's a bit weird, but it is absolutely correct, which is elemental length AB equal to DL. Now I always recommend that compare and study. So see, in the previous one, when we see, it was like this one. O is its center, the specified point, and it is connected like this to elemental length AB. Here the elemental length is above and the specified point is here. It is connected this way. Okay, so again the angle between them is 90 degree. In circular coil it is always 90 degree. Here also it was 90 degree. Even here it is 90 degree. Basically the theory behind this is that this is the tangent drawn here, so tangent always it is 90 degree, so it is 90 degree. Okay, now as I said, let Cp equal to, yes, the midpoint C is connected to P such that Cp equal to R. Okay, Cp equal to R. Now here comes the use of R. P is connected to the midpoint of the elemental length AB, which is C, such that Cp equals to R. Okay, now angle between them is 90 degree as they are tangent. So according to Biot-Savart's law, let us not draw the entire figure now. Simply according to Biot-Savart's law, right now dB will be equal to mu naught by 4 pi I dl sine theta by r square. Theta is 90 degree. Okay, so it will be 1. So dB equal to mu naught by 4 pi I dl by r square. This is equation 1. Now see, now the figure becomes a bit complex. Okay, we'll just assume that let A dash B dash is another elemental length, which is dl, same length, but at the diametrically opposite side of this AB. Okay, its midpoint C dash is again connected to this point P, and even its radius is R. Okay, now on resolving this, first of all let me clear that this one element at this point it is dB, the flux density is dB. मतलब कि इस पॉइंट पे P पे जो एलिमेंटल लेंथ के कारण, दिस एलिमेंटल लेंथ के कारण यहाँ पे जो फ्लक्स डेंसिटी है वो है dB. ठीक है, but due to this elemental length, the flux density which is at P, it is dB dash. See, we are calculating the flux density at P due to the entire length of the conductor, but before that we need to calculate due to the elemental length, small elemental length. So due to this small elemental length, the small flux density is dB, and due to this small elemental length, the flux density is dB dash. Okay, on resolving dB and dB dash, since this is alpha, okay, this angle is alpha, you need to remember that now. Now there is no other way, you need to remember that this is alpha. So due to, on resolving this is dB and dB dash, we get the vertical components as dB cos alpha and dB dash cos alpha. These are the vertical components. This way dB cos alpha, and this way dB dash cos alpha. Okay, these are the vertical components. They cancel each other. Obviously they are opposite in direction, they will cancel each other. Then we get horizontal components as dV sin alpha, and one more dB dash sin alpha. and these both are acting like along the same plane. Okay, now let me revise this whole figure again. This is the circular coil, current is flowing through it, P is the specified point connected to the elemental length, which is R. Again, let A dash B dash be another elemental length, small elemental length at diametrically opposite side. This is also connected to P with and the angle between them is alpha alpha. Okay, so due to this the magnetic flux density is dB. Due to this the magnetic flux density is dB dash. On resolving dB we get dB cos alpha and dB sin alpha. Obviously dB cos alpha, dB cos alpha is the vertical component up here. Okay, and the horizontal component is dB sin alpha. Again, for dB dash it is the vertical component dB dash cos alpha, and horizontal component as dB dash sin alpha. So basically these both will cancel each other. So the net magnetic flux is obtained by dB dash sin alpha. Okay, it's the result of dB dash sin alpha. So we'll get the dB in this direction. Okay, this is very easy, dB and dB dash. See, let me clear this figure again because I know you're getting confused. So see, due to this elemental length it is dB dash, due to this elemental length it is dB. On resolving we get dB cos alpha, dB sin alpha. On resolving dB dash we get dB dash cos alpha, dB dash sin alpha. These both cancel each other and only this remains as the effective magnetic field, effective flux density. So we get the flux density to the entire length of the conductor by integrating this dB sin alpha, not this, because these both are cancelling each other. So we'll integrate this to get the final result, either this or either this. कोई सा भी कर सकते, dB dash cos alpha भी sin alpha भी कर सकते या फिर dB sin alpha भी कर सकते. For ease we take dB sin alpha. Okay, so let us integrate 0 to 2 pi a, the respective limits. As I said, it is about the perimeter. See, starting from 0 like this, 2 pi a to the entire length of the conductor. So 2 pi a, it is dB. No, as I said dB sin alpha. Here I made a mistake. dB sin alpha. I said you see, again we'll compare and do. There it was directly dB. Okay, integrating dB. But here it is integrating dB sin alpha, because dB cos alpha cancelled each other. Only remaining was dB sin alpha. So due to this the effective magnetic field intensity is being produced. So we'll integrate dB sin alpha to get the final result. Now see, dB sin alpha, dB ka value already we have in equation 1. Okay, mu naught by 4 pi I dl by r square into sin alpha. Again the constant wala चीज़ यहाँ पे आता है, म्यू नॉट बाई 4 पाई constant, I constant, r square constant, sin alpha constant, because alpha is always gonna remain constant, it's never gonna change. So again the remaining will be only this much, rest all will be out. I by r square sin alpha. Okay, again we'll do that respective limits one thing. So see, to be mu naught by 4 pi I by r square sin alpha. Again limits, पहले ऊपर वाला limit L 2 pi a and 0, 2 pi a पहले 0. So I'll write directly, not much precise, I did it earlier as well. So sin alpha into 2 pi a. Okay, this is pi. Now see again the calculation thing. After doing calculation, this, okay, I'll show you. Equivalent 2. So after doing calculation we get mu naught I a by 2 r square sin alpha. This is our second equation. Okay, now here comes a bit complex thing. Now till now we understood it was not that complex. The figure was a bit complex, I know, but not, this calculation was not that complex. Now see, this is not our final result. Obviously we got the magnetic flux density to the entire length of the conductor, but this is not convenient enough. ये easy नहीं है calculate करने के लिए. So now what we do, we substitute the value of r, okay, r and sin alpha. Now in this whole thing you need to remember only few things. Rest all calculation you can do, but only remember few things. here this resolving one and this one. We need to calculate the value of r square and sin alpha and substitute it for our convenience. ऐसे यहाँ तक कर देंगे 3 marks आ जाएगा, 3 marks. But for convenience we'll do. So now see, we'll see the figure, okay? We'll see this figure. OP, okay, see, OPC. In triangle OPC, we see that we need to calculate sin alpha and r square, okay? We remember sin alpha and r square. So see, sin alpha will be P by H, okay? P by H1, H is what? This, you know? This. So P by H, it means A by R. So in triangle this, sin alpha equal to A by R. Sin alpha, we got the value of sin alpha. Now the value of R. In the same figure we see, using hypothesis, So in this same figure we see, using the Pythagoras theorem, we calculate r square equal to a square plus x square, okay? So see, we got sin alpha, okay? We need to calculate the value of sin alpha and r, okay? So sin alpha we got, now r. Now in this same figure I forgot to tell you something, that this x is the distance between the P and O. It means x is the distance of the specified point from the center of the circular coil. Never forget any detail in the figure. So it is very easy, a r x. So r square plus a square equal r square equal to a square plus x square. Pythagoras theorem, easy. Let's do it in the next page. So r square equal to a square plus x square, okay? So r will be root under a square plus x square. It will be a square plus x square to the power 1 by 2. You know the indices, okay? Now we got the value of sin alpha, we got the value of r. Now we need to put it in that again. So it was b equal to mu naught ia by 2r square, ia by 2r square sin alpha. This was the expression. We need to put the values of r and sin alpha. Sin alpha we have a by r, okay? So it will be mu naught ia by 2r square. Sin alpha means a by r. It became mu naught ia square by 2r cube, okay? So it becomes mu naught ia square by 2. Now we'll put the value of r. R means a square plus x square, to the power 1 by 2. It is cube, so whole cube. So the final expression will be mu naught ia square by 2. Now see, it will be 3 by 2, 1 by 2 into 3, 3 by 2. So a square plus x square to the power 3 by 2. This is the basic expression for magnetic field, magnetic flux density due to the entire length of the conductor along the axis of the conductor carrying current, the circular coil carrying current. Now the revision once again, it was very easy. Circular coil figure, see, dB and dB dash, dB resolutions dB cos alpha and dB sin alpha, dB dash का dB dash cos alpha and dB dash sin alpha, dB cos alpha, dB dash cos alpha cancels each other. The effective will be dB sin alpha and dB dash sin alpha. So we can take any of them to integrate. So we took dB sin alpha. Again dB का value पहले से था हम लोग का according to Bart-Savart's law, and then sin alpha. Integrating we got this value, integration after integration, and then I said you need to remember. What you need to remember, the another thing is to put the values of r and sin alpha. Sin alpha from that from the triangle. So sin alpha will be a by r. So a by r, and r will be a square plus x square. So r we got, sin alpha we got. Again putting the values, we calculate the final value. And as we did in the earlier one, after calculating the final value, we wrote that if there was n such circular coils, then its value will be this. Again we can do the same thing. If there are n such circular coils, then its value will be just multiplied by n, u naught ia square n, and again 2a square plus x square to the power 3 by 2. This is the required value, okay? Now see, special cases is not that much necessary, but if you want to see the special cases, then it's not pretty tough. It's only that if the radius of the circular coil is very small, obviously if the radius of the circular coil is very small, see, radius of the circular coil is a. If the radius is very small, then a square plus x square will be nearly equal to x square, okay, because a square will be negligible. Radius of circular coil is small, so it will be nearly x square. So obviously the expression will be u naught I a square by 2x cube. This will be the expression. First special case. Second special case is that if the second special case is related to the first application. The first application was that center of circular coil, okay, carrying current, at the center of circular coil carrying current. So this second special case says that if the specified point P, it would lie, this specified point P, it would lie at the center of the coil, this point, if it would lie at this, then what would be this flux density? Okay, now see, if it would lie at the center of this, then obviously the distance x would be 0. So now x will be 0, so a square plus x square will be a square. Now put the value there and you will get the same expression. The expression will be mu naught Ni by 2a, and this is the same expression which we got in the first application. See, which we got in the first application. This is because this was also about the magnetic flux density at the center of the circular coil carrying current, and this special case is also saying that if the specified point, if it would lie at the center of the circular coil, then what will be the flux density? Obviously it will be the same. So this is all about the two applications of circular coil. The rest will be dealing in the next class.